All right, who's ready for some machine learning at 9:15 in the morning? Everybody go out party last night? No, right? Nobody. It's my first time in Argentina, and consequently Buenos Aires. I figured out it's my 40th country that I visited. It's a bit of a round number, so that's awesome. I figured if I get on a boat to Uruguay, I'll be 41st, so kill two birds with one trip. But let's get to the topic at hand. So small data machine learning. It's not really meant to be a comprehensive introduction, but rather just get your mind into machine learning and what it can do, and so you can go investigate some more stuff. I'm just going to change one thing here so I see my notes. Have any questions like that are related to the immediate slide that I'm showing? Raise your hand. Otherwise, I'll try to leave some time at the end. So I work at this company called AppDynamics. We're all superheroes because our customers use our software to keep their mission-critical applications up and running. We have some very clever stuff that figures out what goes on with your app in production environments and immediately reports and gathers all kinds of info for you. If you want to see what it looks like, come find me afterwards. It's pretty cool. I like to travel, although in this photo, the projector is kind of dark. But I'm in Iceland in front of a big geyser. I like to take photos in Hong Kong. I like to drink beer. I like to make beer too. So if you're interested in any of that, come talk to me afterwards. So, fair warning, this will involve some math. Sorry about that. But it's not just some math, it's awesome math. It lets you do some interesting stuff. Now, this talk was sort of prompted by some work I did for my own benefit, and I'll explain why. I don't know if you know this, my Twitter name is @A. Shocked? I got it in October 2008. I had a different account earlier, but then another friend of mine who has a single letter name asked, do you want this one? And stupidly I said yes. And I'll explain why. It sort of came with some fame. I don't know. The Atlantic magazine decided to do an article about single letter Twitter names from A to Z. I'm not sure why that's interesting, but they the call and everything. Wall Street Journal came and did like a whole article. People don't have anything else to write about. Seriously, Wall Street Journal. Comes with some followers. I have like 50,000 plus followers. I don't know who these people are, what they do. Hey, seriously? Anyway, also, since I have such a short Twitter name, people can use the maximum amount of reply space to reply to me, right? 137 characters. It's a favor. Comes with a lot of cons though, and I'll show you what it looks like. This is what my reply stream looks like. I don't know if you can read that necessarily, but it's all a bunch of garbage. Right? I can't even visually filter it just to scroll through and see what's actually the real reply. So if you try to reply to me right now, or actually without the software that I've written, I would just ignore it. And I could have done some like simple stuff that hard-coded rules, like, oh, if it has Japanese characters, just throw it out or something, right? Like they wouldn't be very robust. And you can see like how frequently those happen. This is all within like span of a minute. So they just like 500 in an hour or something. And this led me to work on a software because I was really annoyed. And the best way to develop something is by annoyance-driven development. You're really annoyed about a problem, you go ahead and code it up and hopefully help yourself and others. So, machine learning to the rescue. I was always interested in machine learning. This was finally a chance to apply it to something useful, I guess. And so I made this thing I called Reply Cleaner, which sort of cleaned it up a bit. So now you see it's not like every 4 minutes, it's like within a span of a couple hours, I can actually scroll through this and it filters out like 90% of garbage right away. So it has some false negatives, but it's still much more visually clear. And it uses this trained model to automatically classify the tweets into good and bad ones. And when it finds a bad one, it blocks that user, because that's the only way on Twitter to remove something from your reply stream. You can't just say, oh, remove this one tweet, and that's it. You have to block the person. And I think I accidentally blocked Mariano once. Actually, not me, my software did. I unblocked him since. But then I can actually, and the advantage of blocking at the Twitter level, like, because this hooks into the streaming Twitter API, I can use any client, web, mobile, whatever, and it cleans it up automatically. So like this person was replying to me, and I can actually read and converse with them now. Of course, there's other interesting stuff where people completely misuse @a, like saying, "Hey, what are you doing today? I'm at a bar," and things like that. It's just stupid. And then you uncover other gems like this person. Right? Or this. What? I still hate humanity. All right, so enough jokes, I guess. Let's get to machine learning. So, there's no like exact definition of machine learning, but I like this quote from Arthur Samuel that says, "It's a field of study that gives computers the ability to learn without being explicitly programmed." And just if you paraphrase, it's basically it's a construction and study of systems that can learn from data without you explicitly telling what the rules are and things like that. And they're all around us these days. I mean, they do spam filtering. It's like Gmail. I went into my spam folder, and I don't usually look at it, right? But it just filters out all this garbage. Recommendation systems, like on Amazon, which may be good or bad, depending on whether you like shopping or not. When you go look at 50 Shades of Grey once, and then it suggests all kinds of other books to you. Automatic machine translation, which is what Google does for a lot of their language pairs. They don't actually have like rules that are saying, okay, if this is the grammar of the sentence of type A, then do this. They statistically analyze the whole bunch of data sources with English and Chinese, Japanese in this case, and figure out what maps to what, and then it just magically does it. Things like clustering, where it automatically clusters related articles together. So there's some articles about chimps or deadly smog in Beijing. And many more. Medical diagnoses, detecting credit card fraud, and a bunch of other applications. So broadly, machine learning can be divided into two areas. There's the supervised learning, which is a little more rigid and rule operated, where it works on a labeled data set. So you have some inputs and they have labels, things like, oh, this is the number of words in this tweet, or other things, and you have some desired outputs saying, okay, is this actually a bad tweet or not, or is this spam or not? And training maps those inputs to the outputs. Examples of these are things like regression, where you use some inputs to predict like house prices, like depending on the size of the house or where it's located and things like that. Or classification, which involves anything where you want to assign an item to one of possible categories. And then there's also unsupervised, where it's unstructured. The algorithm just takes the data set that has no labels or any like outputs, and it tries to figure out what the structure of that is. So that's what things like clustering do, where they try to group items together just based on the contents of the data. And for this talk, we'll just be covering classification, which is like one of the simpler algorithms, and it's a supervised learning process. So before we dive into the actual stuff, we need to talk about features. And for the purposes of machine learning, the feature is defined as an individual measurable property of some phenomenon that you're observing. So it's usually numeric. It's like a floating point or integer number. And the easiest way to think about features is you look at like nutrition facts on a box or something, right? And it tells you, oh, it has 520 calories and 27 grams of fat. Scary. And carbohydrates and proteins and vitamins, and each one of those is a feature with some associated number, right? And when you put them all together for a specific product, let's say, you get what's called a feature vector. And it's a set of features for that observation. Just think about it as an array of numbers, right? Each one that defines some sort of, or represents some sort of feature. And, if we're talking about predicting house prices, let's say we have features like, okay, number of rooms, how many square meters it is, how old the house is, does it have a yard or not, which is in case is a Boolean feature, and we can represent it just 1 and 0. And corresponding to these features, you would have what's called parameters or weights. And these weights, you don't specify those. That's the job of the algorithm, to figure out what the weights are for each feature. Because when you put them together, and so the top one there is for padding. It's called a offset or bias, or it just simplifies calculations when you look at it. Then you do what's called a dot product. Familiar with dot products from math? Yes? It's not that hard. It's just, I'll show an example in the next slide. But when you multiply them out with a dot product, you get your prediction of what the price of the house will be. In this case, something like that. And depending on what your model is, this could be in dollars or pesos or cents or whatever. So dot product, let's say X is your input. That's what we had on the left, set of feature. Starting, 1 is our padding one. And then X1, X2, and so on. And then theta is the parameters or weights, right? Corresponding to each one. And all you do is just, for dot product, you go through and multiply them, 1 times theta 0 plus X1 times theta 1, and so on. And that's your dot product. All right? Now, the way pretty much all these algorithms work is you have some sort of training data that comes in, and then you apply a learning algorithm, and there are many learning algorithms. We'll talk about just one in this talk that's sort of easier to intuitively understand and represent. And the job of the learning algorithms is to come up with what's called a hypothesis, or it's also called decision function. And this hypothesis represents what the system has learned so far. Most of machine learning is an iterative process. You don't just run it once and it gives you the answer. Well, if it comes up with a hypothesis right away, you do it over and over, and it incrementally gets closer to the correct or the most likely estimate or prediction. So there's 20,000, 50,000, 100,000 steps. But we think computers are fast, right? And when you come up with this hypothesis, you can apply it to the new data and get your prediction for things you're looking for. And hypothesis is usually described or represented as this function, right? It's called h, and it's applied to input data, which is x. That's your set of features for all your data. And it's parameterized, right? It has these weights. And the task of the algorithm is to determine these parameters of the hypothesis. And once it does, You apply it to some sort of a new set of data, and you get your prediction, which we'll call Y. Everybody with me so far? Questions? Okay. So, the simplest algorithm that you can talk about for like supervised learning is called linear regression. And it basically models a relationship between some sort of dependent variable. In this case, let's say I wanted to model, I like whiskey, right, which I do. And this represents a set of whiskeys in my cabinet, which I wish I had that many. But I wanted to figure out, okay, so I have this whiskeys of various ages, and I know how much I've paid for them. Can I predict for a new whiskey that I look at the store or whatever, like what it's going to cost approximately, right? And in this case, the dependent variable is the price, which is what I'm trying to predict. And the explanatory variable, or independent variable, it's X. In this case, it's whiskey age, right? And linear regression simply tries to map a line through that, right? Tries to figure out what's the best fit for the relationship. What is the slope, and where the line is located. And let's say it comes up with a line like this after a certain number of iterations and so on. And then, let's say I don't have any 25-year-old whiskeys in my collection, but I'm trying to figure out what it might cost. So once you have this line, you just basically trace it over, you're doing it manually, and to the left, and it's going to be about $135, $140. Okay, maybe not. Maybe I won't buy that one. But you can see that once you come up with this prediction, with this model, then you can pretty much predict with a certain degree of accuracy what the prices will be. Now, linear regression is good for things like predicting prices or temperature or whatever, but it doesn't work very well for classification, where you're assigning things to one of the categories, right? Or especially to binary classification, where it's just 0 and 1. And the reason it doesn't work well for that is because its output is unbounded, right? It can be like minus a million to a million, or whatever that line comes out to be. And you can threshold it. You can say, okay, if the result is greater than 50, then it's 1, or if it's below 50, then it's 0. But it doesn't, in practice, work for that. So instead, people use what's called a logistic regression. And it's represented by this function, which is 1 over 1 plus natural base logarithm to the minus z. And it's not that hard to sort of understand, but it's called a logistic function or a sigmoid function because it looks like letter S, right? And if you notice that the further it goes to the right, it approaches 1, and the further it goes to the left, it approaches 0, right? And it crosses 0.5 at the origin. And the beauty of this function is that you can use this to do binary classification, right? You can just say, like, oh, since it's bounded by 0 and 1, I'll just choose some threshold. If it's over that, then it's 1. Then it's below that, and 0. And another question you might have is, what's that z there, right? Well, that's our dot product, the prediction that we made, the linear prediction that we tried to do. And this function takes this unbounded input from minus a million to a million or whatever and transforms it into a bounded 1. And then what the hypothesis looks like then, if you substitute that in, is something like this, right? And what this really tells you is what is the probability that y equals 1, which is what the probability that this is spam, what is the probability that this is a bad tweet, what is the probability that this is some other binary category for a certain input. So if you're trying to do the spam classification and if X your body of text, you can do something like, oh, y comes out to be 0.7, means there's 70% chance it's a spam. And you can threshold that yourself, saying, I'm comfortable with 70%, probability that it's spam. Or maybe I want to be really certain, maybe like 95%. Anything below that, I'll just let through because I don't really want to throw out much stuff. So this is intro. Now, let's talk about building the actual tool and how that worked. So there's some theoretical background here that I went through. How do you actually apply that? Well, in order to do any sort of machine learning, you need initial training data, or corpus, as they call it. And it's some source data used for training and testing the model too. And the way I collected this corpus is, well, I have Twitter, I have Mongo, or other database. I use this library called Firehose, which is, PHP people like to use PH for F instead of F for everything, I guess. So it hooks into this Twitter streaming API, and I just saved all my reply stream for 2 weeks into a database. I forget how much it was, 8,500 tweets. Yes, 8,500 tweets, which is, I wish I had more, but even with all that stuff that's coming through, people still don't use EDA that much, apparently. So I have my 8,500 tweets, and my next task was feature identification. And this is where you go through and you decide what are the relevant features that I want to use for training and classification, right? Like in the example, look for house prices prediction. It was, square footage, how old the house was, and all that stuff. Well, what do you use to classify a bad tweet from a good one? The two rules you want to follow when you select features, the main ones, are that they have to be independent and discriminant. Right? So independent means feature A, you have two features, feature A and feature B. They should not occur together too often, right? Because if they occur together very often, you can just throw one of them away. It doesn't really help you to classify stuff. You already have the other feature. So you want to have them not co-occurring too frequently. And discriminant means a feature should provide some uniquely classifiable data to help you with the classification. So, like choosing what letter a tweet starts with is not a good feature because it doesn't really give you any information, right? If it starts with letter C, is that a good or a bad one? Who knows? But if it has 20 mentions, or 20 hashtags, that potentially is a useful feature, right? So I went through and I tried to identify what are some possible features I can use for classification. What I came up with are things like that, right? I noticed that if add A occurs at the very end of the tweet, more likely than not, that was a bad tweet. Or if it was some sort of truncation where it was like add A ... Or if it's a very short one, sometimes people just put add A and that's it. And Twitter filed for IPO too. Can't you just clean this stuff up first? Number of user mentions in the tweet, number of hashtags, which I already mentioned. Language is very important, as I found out, and I'll go into that in a little more detail. And a few other ones. So I came up with these possible features, and then for each one I went through and I wrote a little function called extractor, which I pass it a tweet. It runs some sort of regular expression or whatever, and some other things, and gives it back that numeric value for that specific feature. Which were floating point, just to standardize on that. It makes math easier. And then what you do once you have these extractors for each feature, you take your corpus, which is your source data, right? You run it through these extractors, and you end up with a whole bunch of feature vectors, which you can think of array of arrays, because for each tweet in the corpus, you're going to end up with an array of features for each one to be created. So it's going to be like a big matrix. And save it to database or somewhere just so you have that. Now I mentioned language, which is probably what I spend the most time on. And what I found out is a very high correlation between the language of the tweet and whether it was bad or good. If it was Indonesian or Tagalog, it's garbage, completely. Like, I wouldn't even try to mark it as good. I went and counted top 12 languages in the corpus, And that's what it was. Like, top one was Indonesian with 3,500 tweets. English was after that. But I think the reason it's so high is because Twitter just mislabels some of that stuff. Also, you can't trust Twitter to label a user's language correctly. And I'll explain what I did for that. And Tagalog was next. Spanish was there too. But there's like Somalian, right? I guarantee if somebody's tweeting me Somalian, I'm just not going to be interested. I mean, I can understand some French and some Spanish, but not Somalian. So I had to do some language detection. Like I said, you can't trust the language field in users' profile data. So what I did is use a couple of libraries that do n-grams, like 2-3 character sequence detection. They use that combination to figure out what language it might be. And that has its own error rate, so it needs some post-processing. But I used, there are a couple of libraries that can help you do that. One's in pair called text language detect, and the other one's in PECL called textcat, which is faster. And they give you back the guess for the language along with a probability that is that language, or give you like the top 5 or something, and it's up to you to decide whether you want to use that or not. Like I said, you need some post-processing, especially for English. So there's this thing called English not English again. So before I do detection, I remove all the links, I remove all the mentions, just to give it pure text. And I run language detection. And if it's unknown or some sort of low weight, I'll just pretend it's English. Like, there's not much I can do after that. If it's, however it says, if it's English or some sort of, French or something like that. For English, I can do a little better to make sure it's English. I can tokenize it into words, and then use English vocabulary and just throw out the ones that are English words. And then you are left with some uncertain ones. And then you run a thing called parts of speech tagger on it, and it figures out what part of speech it might be, like noun or verb or whatever. And if it's certain rules where you, like in English, the verbs have ed or s on the end, depending on past tense or present, third person, or whatever. Then you run a stemming algorithm, and if the result of the stemming algorithm is in an English vocabulary, then you also throw that away. And then you do a little bit of a calculation to figure out, well, if I have anything left, how many words are those compared to the original one? And if it's less than 20%, I'll just pretend it's English. So it's a lot of it is heuristic based, but after a bit of trial and error, I came up with a set of these rules that seem to help with my corpus. So let's say language detection is done, I have my features, right? I still need to know the labels for the original tweets, whether they're good or bad. I need those for training. So I wrote a little tool where I pulled up, 15 tweets at a time, and I had to go through and manually say that's good or bad. Right? That's a lot of grunt work, but it needs to be done. And so, like in this case, oh, somebody's actually replying to me. For real, this Beer Norway guy, so all right, let me mark that as good. And I did for English and French and maybe some other ones. I didn't bother with the rest, I just marked them all as bad. But after this, you have everything you need for training. You have your input, which is feature vectors that you derive from the corpus. And you have your labels, where they're good or bad, right? So now we need to run the actual algorithm to figure out those weights and to create the model. But before we do that, we need to address a little thing called bias correction. So bias correction happens when the ratio of your bad to good labels is way off, right? So in my case, after I was done with labeling all those tweets as good or bad, 99% of those were bad, right? Which is sort of what I expected, but the problem is that less than 100 tweets were good, and running a algorithm on that, as it was, would not produce good results. It just didn't have enough of the good data to operate on. So we need to adjust the bias so that they're about equal size, right? And how do we do that? Well, there are two ways of doing it, 2.5 actually. So there's a thing called oversampling, where you take the smaller group, in this case good tweets, and you copy them, right? You multiply them until you equalize it with bad. The problem with that is because the bias is so high, you would have to copy each good tweet like 100 times in order to sort of contribute something, right? But because there's so many copies, they're only contributing a lot of variance to the good category. And then there's the opposite thing called undersampling. And undersampling, you basically look at your bad category, the large category, which in this case was bad, and you just drop, a certain percentage of those tweets to equalize it with a good one. The problem here was that if I drop tweets to equalize with the good ones, I'd end up with a corpus of like 200 tweets, which didn't help anybody. So there's this thing called synthetic oversampling. And what you do in this case, once you have an understanding of the structure of your good tweets, like, oh, it's mostly people who use one or two mentions, maybe a hashtag or something, and it's in this language and so on, you can sort of synthesize good vectors, right? You can do some random number picking and create those vectors by, because you know what constitutes a good tweet, and you do some random selection. So in this case, like, I'll just pick a number, from 0 to 1, and if it's over 0.9, I'll consider that a good language. And if it's, then you do another pick a random number, and you say, okay, this one we're going to have one hashtag, and so on. And you basically fill in these feature vectors that you classify as good ones. And you do it a bunch of times. After I ran this, I basically increased the good category to be almost equal to the bad one. So once you have the bias corrected in your corpus, then you can actually do the training, right? So at this point we have the training set. We know what algorithm which decision function I'm going to use, which is the logistic regression with that nice S-curve. How do we actually determine the weights parameters? So the primary thing to understand here is what's called the cost function. And this measures how far the prediction that you make is from reality, right? If the prediction is accurate, it's going to be small. If it's not accurate, it's going to be large. And this cost depends on the parameters, right? And the less the cost, the closer we are going to be to the ideal parameters for this model. So, math, right? And all this says is that the cost function is basically for each prediction and for each label that you have in your data, we compute this cost and we sum it up and then average it out over all the inputs. And for the logistic regression, the cost, you don't need to copy it or look at it too closely, but if the label is 1, which is let's say good tweet, then it's minus log whatever, and if it's 0, it's that function. But the important thing is to understand what these graphs look like, right? This is logistic cost. So the one on the left, where it says, let's say it's a good one, right? The closer we get to the correct guess, the closer it gets to 0, which means cost is 0, it's great. And the closer it gets to the wrong guess, it's like infinity. We're penalizing the algorithm very harshly for not guessing correctly. And the same for the opposite label. If the correct guess is supposed to be 0, great. If it's guesses incorrectly, we penalize it again. And the whole idea is you want to minimize this cost, right? And how do you do that? Well, there's a thing called, which is, you might have heard about it or not, it's called gradient descent. And the idea is that, let's say this is a graph of your cost function, right? It has hills and valleys and so on, depending on the combination of parameters. And what you do, the intuitive way to understand it is, let's say you're standing on a hill somewhere, right? And you want to get down to the river, down to the valley somewhere. And what you do is you sort of look around and you find a direction that, if you take a single step, will give you the most descent, right? You take a step. And then you look around again. Oh, actually, I need to go this way now, right? And you keep repeating it over and over until you actually descend to where your target is. Another way to think about it is if you put a ball on top of the hill and let it roll, it's going to roll somewhere down here. It may not be the most optimal way, but it will get down there somewhere. And the same thing with this algorithm. You randomly start at a certain point, you pick a starting point, and then you do certain calculations to figure out which way it should descend to get to the lowest cost. And it looks something like this, where your theta is one of your weights, right? This is your parameter. This is a learning rate. And it controls how big of a step you take. If it's big, then you have very aggressive steps like that. Change your parameters a lot, but the danger is that it may not converge exactly. You may skip over the lowest part. And if it's too small, then you have very tiny steps and it runs for a long time. Now this scary looking thing is our slope, right? It's how steep the descent is. And the overall update algorithm, which looks something like this, right? If you just substitute everything in and hand wave a little bit, you have your parameters, you have your learning rate, and then you go through this function, figuring out the cost and multiplying things out. And once you program that in, it's not that complicated. But the important thing is that you have to update your weights simultaneously. You can't be like, oh, I updated weight 0, and then I'm using that weight to calculate the next one, because that creates a feedback loop, and that's not good. So just as an example, because the first time I gave this talk, people were like, okay, it's math. Can you actually give an example with numbers? I'm like, sure I can, okay. So let's say we have 2 feature vectors, right? And one is the padding. It's very simple. There's only one feature. I don't care what it is. The first one has 12. The other one has minus 3.5. Okay? And we'll label the first one bad and the other one good, right? And our initial starting point, we just randomly say for the weights, is 0.1, 0.1. All right. And so, in learning rate, 0.05, right? So, calculate the hypothesis function, where we do 1 over 1 plus e, and we do the dot product, right? We look at 0.1 times 1, plus 0.1 times 12, and all that stuff, right? So, and the hypothesis for the first one comes out to 0.786. And if you do it for the next vector, feature vector, you get 438. And this is where I update the first weight. Where's that scary looking function, right? We'll just substitute everything in. We multiply that out. There's the learning rate and everything. And if we actually substitute the numbers in, we come up with 0.88. And if we do the same for T1, it's going to be 0.305. So after you run this once, the new guesses for the weights, this is your theta stuff, is 0.88, 0.305. And then you repeat many, many times. And eventually, if your learning rate is, not too large or whatever, you'll come up with the optimal weights for this model, right? And then that's basically the training of your model. Now, there's another thing called cross-training, which is once you do this training of your model, how do you know it actually works? Well, it's just numbers. Intuitively, you don't know whether it'll work or not. And this thing called cross-training, which is used to assess the results. And what you do is you take all of your data that you collected and you split it into training portion, and test portion, right? And you train the model on the training portion, and then once you get your weights, your model, then you use it on the test set and repeat it multiple times. What's very common to do is to just randomly split your data multiple times. You just take 80%, goes to training, train it once, you get your weights, then you test it. And you repeat it until results are basically good enough. You pick the best parameters that you come up with, And that's it. That's your result. So then you put it all together, right? Let's use my example of classifying tweets. Once you struggle with Twitter's API enough and tear your hair out, you actually get to the fun part where you load the model. So we have these weights, especially if you have a lot of features, you can just load them from database or whatever. I also had some hard-coded rules where, I mean, like I said, if I know it's Indonesian, like I just don't look at it, right? But things like truncated retweets, where people do that stuff for some reason. If I mention any of my friends in my, if somebody mentions my friends in their tweets, usually it's probably okay. Or tweets from friends, right? And then you actually do the classification, which is the moment we've been waiting for, right? So we take our input tweet, we run those extractors for features, it gives us the vector, we run them, we have our weights, right? And then we just apply that hypothesis function, and it gives us, you know, whether it's good or bad, depending on the threshold we picked. So we have our hypothesis, right? We have our dot product of features and weights. And if you substitute that in, again, it looks something like that, and then gives you a number from 0 to 1. And depending what threshold you picked, bad. Ban the person, and you'll never hear from them again unless it's somebody you know, and then they complain. I use something like 0.9 to reduce false positives, so only if the algorithm is really sure, then ban somebody. Otherwise, I don't mind looking at some more garbage, but it's up to you. But yeah, you extract features, you run the model, and you act on the result, which in this case is blocking. And I also save all the tweets that I block, or tweets that I acted on, to the database for future analysis, because maybe there's some useful data there that will help me to get some more features and things like that, which is where lessons learned come in, right? Well, number one lesson that I learned from working on this is Twitter's API is a pain in the ass. Anybody work with Twitter API here? Yes. Is it good? No. No. There's connection handling problems. There's very complicated back-off rules where don't access us too quickly or we'll ban you, and undocumented API errors, all kinds of stuff. It's just not good. Blocking is really the only option, right, to get rid of stuff in your reply stream, like I mentioned. I wish they had a way to just say, okay, don't show this tweet, but they choose to concentrate on making their API bet instead. So you have to err on the side of caution. Another thing I learned is that the streaming API delivery is incomplete, where my script wouldn't get anything, but this tweet would show up in the reply stream, if I look on the web or in mobile, it just didn't deliver it to me. I don't know. I judged my thing, like I said, about 80% effective. I could tweak it more and make it better, but it works pretty well for now. And now the lesson I learned is PHP sucks at mathy stuff. Let's be honest, it wasn't really built to be a computational language of any sort. It's fun to prototype something in it and figure it out, but if you're actually going to use it in any sort of serious manner, there's other things you can look at, which I'll mention. So some of the next steps that I could make to improve this, right? Real-time feedback, where have some sort of app where I can go in, and if it had a false negative or something, I can just say, oh, actually this is a bad one, and it adds it to the model and reruns the training and all that stuff, and it learns from that basically. I could also develop more features. Which ones I'm not sure yet, but things like maybe time of day or some more language-specific stuff. Could do some grammar analysis to eliminate stuff like at a bar or to at a time. Yeah, please don't say at a bar. So I talked about gradient descent, right, where like so it gradually figures out what the optimum is. The problem with gradient descent is it may not always give you the most optimal minimum, but there are algorithms that will. Things like support vector machines or decision trees potentially, where you can just run them once and they're guaranteed to give you the most optimal solution. Now they're more complicated to explain and develop, but there's definitely improvements there. And Twitter has this thing called Clockwork Raven. Anybody heard about that? It's this programmatic interface to Mechanical Turk, basically. So if I wanted to do this manual classification all over again, where I assign labels good or bad, I could like write a whole script that farms out this task to a bunch of humans somewhere. They just go and do this for me, and then the results come back, and it's so awesome. But unfortunately, they released that right after I was done. Figures. I wish there was something like, so Python has this thing called scikit-learn, which is an entire library dedicated to machine learning and scientific computing, and it's awesome, and it's like all in C and runs very fast, and this is what I actually used to prototype stuff before I put it in the PHP. I wish there was something like this for in Peklo or whatever. So, I mean, I'm probably not gonna have time to work on it, but you should go bug some other developers to do this because it will be very awesome. Some of the tools that I use for this, I mentioned Mongo, which is great for tweets because it's all JSON. You just stuff it in there, it automatically understands them, right? The text language detect and pair. These are all links, by the way. I'll post the slides somewhere. You can go actually click on them and it takes you to the right place. English vocabulary corpus, which I used for that language, English language detection. Parses speech tagging also. This thing called SPL fixed array, where, you guys heard of this? It's part of the SPL extension, and it basically gives you a more efficient array representation if you're just using numbers or arrays of a certain size, right? PHP arrays aren't really arrays, they're like linked hash maps, because you can throw strings and numbers and then whatever and delete from the middle, but they're not very optimal for just representing like matrices. SPL fixed array is better. Firehose tool, just to suck things down from Twitter. And then I mentioned Python scikit-learn to validate the results. I also have a link to the code sample, which somebody, when I first gave it to them, they were like, can you actually like have a PHP, give us the PHP code for this? And I wrote a little, like almost a toy sample where I was going to show it, but the projector is kind of dark and it's hard to see. I mean, I don't know. Do you want to try?
Oh yeah, you're right. It's only you make it default, right? That's what I'm trying. Oh, it's blurry. Okay, that's a little better. Yeah.
Anyway, there's a link to it. It's on GitHub, and basically, it shows you how to do some simple classification. Because it only has 3 features, like for the data set, like if I wanted to move somewhere in the world, like what's the likelihood I want to move to a certain city, and I use like average low temperature, if it has an international airport, and like population size or something. And it goes through and like does the gradient descent and everything and figures out like, then uses some test data and so on. So code sample, there's some good things to take a look at if you actually want to learn more about machine learning. Coursera.org has a whole machine learning course, which is what I went through it once, and it's good material. Ian Barber, who is in the PHP community, did a few blog posts about classification and linear regression and things like that. And then there's a site called fastml.com, which also has good blog posts. So, questions, I guess, since we're almost out of time.